Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Come settle in by the warmth here with me tonight. I know you've been carrying something heavy on your mind lately, thinking about all those models you've built over the years, those 40 fraud and risk systems that seem so essential, so carefully crafted for their specific tasks. There's a profound shift happening in how we build AI systems, one that might change everything you thought you knew about enterprise machine learning. Tonight, we'll walk through this transformation together, gently, so you can understand what it means when the single model era gives way to something entirely different. Let's begin by exploring why AI agents need their own form of intelligent guidance to succeed at scale. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep. Throughout history, humans have relied on guides to navigate complexity, much like how a lighthouse helps ships find safe harbor through treacherous waters. Ancient civilizations used the sun and moon as celestial compasses, eventually developing maps, then physical compasses, and today we carry GPS systems that guide our every journey. In the emerging world of agentic AI, we're witnessing a similar evolution, where AI agents hold tremendous potential to transform enterprise workflows, but they need their own form of intelligent guidance to truly succeed at scale. The challenge facing enterprise AI adoption today mirrors the difference between wandering through an unfamiliar forest versus following a well-marked trail with clear signposts. Numerous studies have documented the overwhelming failure rate of AI pilots in enterprise settings, and researchers have identified a key insight. For AI to achieve scalable adoption, it must operate at the very core of enterprise workflows, not just at the periphery where simpler tasks live. Enterprise workflows possess three distinctive characteristics that make them particularly challenging terrain for AI agents to navigate effectively. First, they're dynamic and long-running, like rivers that change course over time, requiring agents to adapt continuously rather than execute simple, one-shot tasks. Second, they involve a vast ecosystem of APIs, databases, and services, creating a complex web of interconnected systems that agents must coordinate across. The third characteristic involves the constraints imposed by business policies and regulations, which act like guardrails on a mountain road, ensuring that agents operate within acceptable boundaries while still making progress toward their destinations. These three factors naturally demand expanded model context from large language models, which state-of-the-art frontier LLMs certainly possess. But this expansion comes with significant trade-offs in the form of increased hallucinations and token consumption. This is where the concept of agent logic emerges as a crucial innovation, functioning much like a GPS system that intelligently guides the underlying language model through the complexity of enterprise workflows. Agent logic consists of software primitives such as knowledge graphs, algorithms, and program analysis libraries that operate within an agent harness, intentionally steering the LLM toward more relevant parts of the workflow while reducing the overall context space that needs to be processed. IBM has tested this approach across 4 particularly challenging domains within enterprise software delivery lifecycles. These domains represent mission-critical workloads where subject matter experts struggle with complexity daily, understanding applications written in legacy code like COBOL and PL1, expediting test generation for developers, proactively responding to incidents while enabling shift-left application resiliency, and automating compliance modernization for critical environments. In the first domain, IBM's watsonx Code Assistant for Z incorporates an App Insights agent that functions like an archaeological team with sophisticated ground-penetrating radar, able to see deep beneath the surface of legacy applications. This agent leverages deep static analysis across applications and stores a pre-indexed representation in a database schema spanning hundreds of interrelated tables with complex semantics, allowing precise retrieval of structured information that's already available rather than regenerating it each time. When applied to multiple mission-critical legacy systems containing up to 1 million lines of code and 1,000 programs, this approach maintains marginally superior application understanding performance while achieving approximately 30 times lower token consumption compared to a baseline frontier LLM-only approach. The agent works with Mistral Medium 250 billion, demonstrating how agent logic can dramatically improve efficiency without sacrificing accuracy. The second domain involves Aster, IBM's proprietary program analysis library that operates like a master craftsman's toolkit, equipped with specialized tools for generating unit integration, ATI, and change-based tests. Based on analysis across multiple developer communities, Aster achieves higher developer ratings compared with various open-source tools or developer-written tests, while delivering superior line, branch, and method coverage benchmarks. IBM has been running Aster in pre-production mode across 75 Java applications within IBM's CIO organization, handling applications with up to 560 classes and 67,000 lines of code using the DevStral 24B model. The steady-state results show 20 to 45% improvement in line, branch, and method coverage, coupled with superior performance compared to state-of-the-art coding agents, while consuming up to 15 times fewer tokens. The third domain addresses incident response and application resiliency, where the challenge resembles managing a vast metropolitan transportation network during rush hour, with multiple interconnected systems that can affect each other in complex ways. Here, the agent logic employs knowledge graphs encompassing entities like microservices, database and middleware services, and monitoring data, coupled with embedded tribal knowledge from domain experts. This knowledge graph approach bounds the LLM to local reasoning for non-deterministic outcomes, using an observability-driven strategy to achieve reduced context space spanning the IT stack and underlying application source code when relevant. IBM's Instana i3 agent, which stands for Intelligent Incident Investigation, leverages this approach to achieve up to 4 times improvement over React agents using GPT 5.1 as measured using IT Bench. When tested with Gemini 3 Flash, the React agent performance improved to within 17% of the i3 agent, while consuming 1.6 times more tokens, demonstrating the cost-effectiveness of the agent logic approach. IBM has extended this methodology to source code analysis using program dependency graphs and bug remediation using inference scaling, showing superior performance for finding culpable microservices and bug repair while consuming significantly fewer tokens. The fourth domain tackles IT compliance modernization, which resembles organizing a vast library where books are constantly being added, moved, and updated according to complex cataloging rules that themselves change over time. Enterprises face increasingly complex and fragmented compliance requirements, forcing teams to spend considerable time manually creating controls, assessments, and remediation plans without centralized knowledge, introducing risks of errors and security gaps. IBM's multi-agent system automates compliance by algorithmically decomposing complex tasks into coordinated steps, using adaptive planning, dynamic decomposition, and workflow sequencing with continuous feedback to iteratively identify fixes and expand assessments. This approach performs 1.3 to 2.0 times better than prior agents using Claude 4 Sonnet with fixed planning strategies, transforming compliance into a continuously guided, self-correcting process. The system dramatically improves outcomes, especially in complex scenarios, boosting success rates from single digits to as high as 80% when working with Claude 4 Sonnet. This multi-agent system, along with 16,000 digitized control mappings, was unveiled as part of IBM's Sovereign Core, integrated with monitoring and drift detection to provide automated evidence generation while ensuring audit evidence stays securely within customer control. Beyond these 4 core domains, IBM has applied similar agent logic approaches to additional case studies, including a configurable generalist agent in healthcare and condition-based maintenance for physical assets with IBM Global Real Estate. These applications demonstrate the broad applicability of agent logic principles across diverse enterprise contexts. The healthcare case study involves a configurable generalist agent that functions like a well-trained hospital administrator who knows all the protocols and can ensure proper procedures are followed regardless of which doctor is on duty. This agent implements policy as code for agent governance, enforced at runtime, independent of model prompts, and without requiring fine-tuning of the underlying language models. Experiments show that the agent's policy system closes large gaps in task correctness, enforcing structured workflows, safe intent handling, reliable tool usage, and controlled output formatting across all model families, including Claude Opus 4.5, GPT OSS 120B, and GPT 4.1, with accuracy improvements ranging from 15 to 26%. The system enforces authority through least privilege disclosure, explicit compliance rules, and human escalation paths. The physical asset maintenance case study addresses a challenge similar to a master mechanic trying to diagnose problems across thousands of different machines scattered across multiple factories, each generating streams of sensor data, work orders, and failure reports. Enterprise maintenance systems collect copious amounts of asset data, but struggle to effectively combine these fragmented signals into actionable insights. IBM's Maximo Condition Insights agent analyzes large-scale asset data across thousands of assets and locations, including sensors, work orders, and failure modes and events analysis, using structured evidence and validation loops to reliably identify issues, prioritize actions, and support decision-making with consistent, traceable insights. The agent employs GPT OSS 120 billion as its underlying language model. When piloted internally with IBM Global Real Estate, the system reduced asset analysis time from 15 to 20 minutes down to 15 to 30 seconds, representing a 97% improvement in efficiency. Coverage increased dramatically from approximately 1% to 30% of assets, spanning over 120 sites and 6,000 physical assets. Using Asset Ops Bench as a benchmark, the Condition Insights agent reduced unsupported claims by 57%, cut verbosity by 35%, improved rule compliance by 30%, maintained near zero contradictions, and lowered token usage by an average of 77%, while slightly increasing diagnostic specificity. The agent leverages a directed acyclic graph to provide structural engineering and operational context. This directed acyclic graph functions like a detailed wiring diagram that helps an electrician understand how different components connect and influence each other, reducing unsupported reasoning that might occur under naive prompting approaches. Constraint-aware prompting markedly improves rule adherence, reduces verbosity, and lowers overall token consumption without introducing system instability. The pattern that emerges across all these applications resembles the evolution from wandering through unmarked wilderness to traveling along well-designed highways with clear signage and efficient routing. Agent logic serves as the infrastructure that enables AI agents to navigate enterprise complexity more effectively, reducing computational costs while improving accuracy and reliability. Just as GPS systems revolutionize navigation by providing intelligent guidance rather than simply showing raw map data, agent logic transforms how language models interact with enterprise workflows. Instead of processing vast amounts of context indiscriminately, agents can focus on relevant information, follow structured pathways, and make decisions based on domain-specific knowledge and constraints. The economic implications are substantial, with token consumption reductions ranging from 15 times to 30 times lower than baseline approaches, while maintaining or improving performance across diverse metrics. These efficiency gains make the difference between AI systems that are too expensive to run at scale and those that can be deployed broadly across enterprise operations. As we stand at the threshold of widespread agentic AI adoption, the lesson from centuries of human navigation remains relevant. The most powerful tools become truly useful only when paired with intelligent guidance systems. Agent logic represents this guidance layer for enterprise AI, enabling scalable adoption at optimal operating costs by simplifying model context and intelligently traversing workflows at their core, much like how modern navigation systems have made global travel accessible to everyone, not just expert navigators. Take a slow breath and let that settle for a moment. This idea that AI agents need guidance, just as ships need lighthouses, and that enterprise workflows are different from the simple tasks that live at the edges of our organizations. You don't need to hold on to every detail about navigation systems or forest paths. What matters is that you're beginning to see how the challenges you face aren't isolated to your work alone. Now, let's turn our attention to something you know intimately: how financial institutions have built those specialized reading rooms over the years, each one serving its purpose, but struggling to share the complete story across departments. Picture a sprawling financial institution as a vast library, where each department has built its own specialized reading room over the years, each with carefully curated books for fraud detection, credit scoring, risk assessment, and customer recommendations. While each room serves its purpose beautifully, the librarians can't easily share insights across floors, and the institution finds itself knowing fragments of each customer's story, but struggling to see the complete narrative that connects every financial decision, every transaction, every behavioral pattern into a coherent whole. This fragmentation has become the defining challenge for financial AI, where NVIDIA's 2026 State of AI in Financial Services report reveals that 65% of institutions now deploy AI systems, with nearly 90% either using or evaluating these technologies, and almost all maintaining or increasing their investment. Yet, as these AI systems scale across more use cases and markets, the complexity grows exponentially, and the inability of isolated models to share context becomes the bottleneck that limits institutional intelligence. Think of traditional financial models like individual craftspeople, each highly skilled in their particular trade, working in separate workshops without windows or doors between them. The fraud specialist examines suspicious patterns in isolation. The credit analyst evaluates risk using different tools and perspectives, and the recommendation engine operates from yet another vantage point, each producing excellent work within their domain, but unable to benefit from the insights their colleagues might offer about the same customer's behavior. Leading financial institutions are now fundamentally rethinking this architecture, moving away from statistical and machine learning algorithms purpose-built for each line of business toward transformer-based transaction foundation models that can learn a single, unified representation of consumer behavior, trained entirely on the institution's proprietary data. These transaction foundation models function as large-scale AI systems, trained on billions of financial events, including payments, transfers, product interactions, and behavioral signals, transforming raw transactional data into sophisticated intelligence that helps firms serve their customers more effectively. Imagine the difference between reading individual sentences scattered across different pages versus understanding the full context of a novel, where each chapter informs your interpretation of every other chapter. A traditional fraud model evaluates isolated signals like a detective examining individual fingerprints, while a foundation model interprets behavior in context, where timing, device, location, and prior activity combine to create meaning, bringing the power of transformer architectures to tabular data and extracting signals that remained invisible to traditional algorithms. Consider how a payment at midnight carries entirely different implications when it's the fourth transaction in 10 minutes, executed on an unfamiliar device, in a city where the customer has never transacted before, compared to a regular monthly subscription renewal. This contextual depth doesn't just improve performance within individual tasks. It enhances understanding across all domains simultaneously, creating a compound effect where insights from fraud detection inform credit decisions, which in turn improve recommendation accuracy. Revolut's collaboration with NVIDIA produced Pragma, a family of transformer-based foundation models trained on 24 billion events across 26 million user records spanning over 100 countries. Built using NVIDIA's complete AI infrastructure, including Hopper GPUs, the QDF library, and Nematron open models running on Nebius Cloud, this single foundation model outperforms specialized task-specific models across multiple fraud detection, credit scoring, and recommendation tasks, while dramatically reducing dependence on handcrafted features. As Tadas Krishunas, head of Group Credit Data Science at Revolut, explains, the transformation eliminates the lengthy feature engineering process entirely, moving from weeks or even months of manual feature crafting to requiring no time for it at all. This acceleration comes from the foundation model's ability to automatically discover and encode the relevant patterns within the raw transaction data, learning representations that human engineers might never have conceived or had time to implement. The fundamental challenge isn't with today's individual models, which often perform their specific tasks quite well, but rather with the trajectory of endless proliferation, like a city that keeps building new neighborhoods without connecting roads between them. Every new use case demands another specialized model. Every new market requires retraining from scratch, and models that cannot share context leave tremendous value scattered across isolated systems, unable to compound their insights into institutional intelligence. MasterCard exemplifies this shift toward unified intelligence, developing a proprietary large tabular foundation model for payments, trained on billions of anonymized transactions today and designed to scale to hundreds of billions across additional datasets, including fraud, authorization, chargeback, merchant location, and loyalty data. Built using capabilities from NVIDIA, AWS, and Databricks, including the NVIDIA NeMo AutoModel Open Library and accelerated computing infrastructure, this model aims to reduce reliance on the multitude of specialized AI models scattered across markets, customers, and use cases. Early testing of MasterCard's foundation model shows it outperforming standard machine learning techniques, with promising applications spanning cybersecurity, fraud detection, loyalty programs, personalization, portfolio optimization, and analytics. Meanwhile, Adyen has deployed transaction foundation models at scale while processing $1 trillion in payments, using reinforcement learning to simultaneously maximize conversion rates and minimize risk for merchants, where even fractional improvements like a 0.1% uplift in authorization rates translate to massive incremental gross merchandise value and substantial cost reductions. The emergence of agent AI adds another dimension to this transformation, with 42% of financial firms already using or assessing systems that can execute transactions autonomously, managing subscriptions, routing payments, and making purchases. Think of these agentic systems as digital assistants that need to understand not just what a customer wants, but the full context of their financial behavior, their preferences, their risk profile, and their transaction history to make intelligent decisions on their behalf. Stripe leverages the NVIDIA and AWS platform to build foundation models that understand the complete context of transactional behavior, rather than simply reacting to individual signals, approach that helped them block close to $112 billion in fraud last year, while delivering an average 38% reduction in fraud rates across their merchant base. This contextual understanding transforms transaction data from isolated events into a comprehensive semantic layer that captures the meaning and intent behind financial behavior. Transaction data represents the proprietary history that competitors cannot replicate, like a detailed diary written in an institution's own handwriting, recording every interaction, every decision, every pattern that defines how their customers engage with financial services. This data already exists within institutional systems. The transformer architecture has proven its effectiveness across domains, and the infrastructure needed to train and deploy these models is readily available through cloud platforms and specialized hardware. The Build Your Own Transaction Foundation Model developer example makes this approach accessible to any institution, enabling teams to begin building transformer embeddings on their tabular transaction data while integrating seamlessly into existing pipelines without requiring complete reconstruction from scratch. Available for deployment on Amazon Web Services using Amazon SageMaker Hyperpod, as well as Nebius AI Cloud. The platform supports the complete transaction foundation model lifecycle, from initial deployment to multi-node training to managed inference. Think of the ecosystem partners as specialized contractors who help institutions renovate their AI architecture without tearing down the entire building. EXL integrates transaction foundation models into its eXellerate.ai platform to unify siloed financial data into a scalable enterprise intelligence layer, while ThoughtWorks helps financial institutions operationalize these models within complex banking environments, integrating them into payment, servicing, and risk systems while establishing necessary governance and AI operating frameworks. GFT IT Consulting demonstrates practical applications by integrating transaction foundation models into their flagship solutions, including Winix, an agentic AI platform used by over 100 financial institutions for secure AI adoption in areas like credit risk, and Smaragd, a compliance engine that reduces false positives by up to 75% for major banks. These implementations show how foundation models transform from research concepts into operational systems that deliver measurable business value. As the financial services industry continues this architectural transformation, the convergence on transaction foundation models represents more than just a technological upgrade. It's a fundamental shift toward institutional intelligence that can reason across the complete spectrum of customer behavior, market dynamics, and risk factors. Like replacing a collection of specialized tools with a Swiss Army knife that's been engineered at enterprise scale, these foundation models promise to unlock the latent value hidden within the vast repositories of transaction data that financial institutions have been accumulating for decades. Rest here for a moment with this image of separate reading rooms, each holding fragments of your customer stories, but unable to see the complete narrative that connects every decision and transaction. This fragmentation you've experienced, this challenge of isolated models that can't share context, it's become the defining bottleneck for institutional intelligence. You've felt this, haven't you, in your own work? Now, let's explore how researchers have been developing new approaches to information gathering, systems that think more like thorough investigative teams rather than single hasty searchers. Picture a detective trying to solve a case by only looking at the first clue they find, then immediately writing their report. That's essentially how traditional retrieval augmented generation systems work. And it's why Google Research has developed something they call agentic RAG, a new framework that thinks more like a thorough investigative team than a single hasty searcher. Traditional RAG systems hit a wall when faced with complex enterprise queries that require information from multiple sources. If you ask about the specifications of a server used in Project X, a standard system might find documents mentioning Project X, discover a server ID buried in the text, but then stop there, unable to take that ID and search a separate database for the actual specifications. This limitation creates what researchers describe as islands of data, where related information sits scattered across different databases, requiring a more sophisticated approach to connect the dots. The result is often partial answers or frustrating not found responses, even when all the necessary information exists somewhere in your organization's systems. Google's new Gemini enterprise agent platform addresses this challenge with cross-corpus retrieval powered by agentic RAG, a system that plans, reasons, and iteratively searches until it finds sufficient context. In testing specifically on factuality datasets like Frames QA, this approach increases accuracy by up to 34% compared to standard RAG systems, demonstrating significant improvements in complex, multi-hop reasoning tasks. Think of multi-agent RAG not as a single search engine, but as an organized research department where different specialists handle different aspects of your query. Instead of one person trying to do everything, you have a coordinated team, each with their own expertise and role in finding the complete answer. The orchestrator serves as the department head, evaluating complex requests and recognizing when a query isn't a simple one-step job that can be handled by basic retrieval. It delegates work to specialized agents, much like a project manager distributing tasks based on each team member's strengths. The planner agent maps out information pathways, functioning like a librarian who knows exactly which sections of the library contain different types of information. If you ask about a project's budget and timeline, the planner decides to check the finance database first, then move to project management logs. The query rewriter acts like a translator, converting your natural language request into multiple, precise search queries. It transforms something vague like, "What's up with Project X?" into specific, searchable terms like status report for Project X Q3 and key blockers for Project X team. The search fan-out agent takes those refined queries and simultaneously sends them to various retrieval sources, collecting snippets of information like a bee gathering pollen from different flowers. Finally, an LLM aggregates all this context to deliver a comprehensive response. The key innovation in Google's framework is persistence, embodied in what they call the sufficient context agent. This component knows when information is missing and continues searching until the context is complete, preventing the AI from guessing or prematurely giving up with, "I don't have enough information." Consider a doctor asking about a patient's discharge medications, dietary restrictions, and any allergic reactions during their stay, specifically excluding certain hospital-only medications, except for heparin IV drip or tenecteplase. This complex, multi-part query demonstrates exactly why simple retrieval systems struggle. The root agent parses this medical request and delegates tasks to subagents, while the planner agent identifies 3 distinct areas to investigate: pharmacy records, nutrition guidelines, and clinical notes. The query rewriter breaks the long, complex request into simple, searchable questions. The RAG agent searches patient records for all query components simultaneously, finding medications and diet information easily, but discovering no mention of allergies in the most obvious files. In a standard RAG system, this is where the process would typically end with an incomplete answer. Think of the sufficient context agent as a quality control inspector standing at the end of an assembly line, examining findings before allowing any response to be generated. This inspector has a systematic process for evaluating whether the retrieved information can actually answer the original question. First, the sufficient context agent evaluates the actual text chunks pulled from the database, reading through specific paragraphs from documents like discharge summary and nutrition notes to see if the needed information is present in those sentences. The system also creates a rough draft response, which the sufficient context agent reviews alongside the original prompt and retrieved snippets. If the prompt asks for 3 things, medications, diet, and allergies, but the snippets only contain information about 2, it flags this as insufficient context. Most critically, the sufficient context agent identifies exactly what information is missing, generating specific feedback rather than just saying this is insufficient. It might note, we have the medication list and low-sodium diet instructions, but we're missing information about allergic reactions or adverse events during the stay. Based on this detailed feedback, the query rewriter creates new targeted searches, perhaps looking specifically for rashes or adverse events. The RAG agent then dives deeper into files it initially ignored, often finding the missing pieces of the puzzle. The sufficient context agent performs one final check, and once it confirms that all required information, medications, diet, and allergy details has been found, it signals that searching can stop. The synthesis agent then writes a clean, accurate summary for the requesting doctor. Google evaluated this agentic RAG system using Frames QA based on the Frames research paper, which contains challenging multi-hop questions like, of the top 2 most watched television season finales as of June 2024, which finale ran the longest in length and by how much? This question requires multiple retrieval steps. First, identifying that the 2 most watched finales are from MASH and Cheers, then finding their running times, and finally, calculating the length difference. Many RAG systems would fail here, responding with something like, despite multiple scans, I found no explicit runtimes. Google's agentic RAG solves this by first searching for the TV shows, then using the query rewriter and sufficient context agent to conduct targeted searches for specific runtime information. The system ultimately determines that the MASH finale ran for 150 minutes, making it 52 minutes longer than the Cheers finale's 98 minutes. The researchers tested this capability at scale using Frames QA's 824 queries and corpus of 2,676 PDF documents, comparing vanilla RAG using Google's RAG engine against their agentic RAG in both single corpus and cross-corpus settings. In the cross-corpus setting, they included 3 additional distracting datasets, forcing the planner agent to determine which of 4 possible databases to search, mimicking real enterprise environments where different teams manage separate databases. The results show that even when the planner agent must select the correct corpus from 4 possibilities, the system successfully routes search queries and answers 90.1% of questions correctly, nearly matching its single corpus accuracy while maintaining similar latency within 3% on average. This demonstrates that agentic RAG can reason effectively over multiple, unrelated data sources, opening possibilities for more flexible retrieval scenarios in complex enterprise environments. The system ensures that AI-generated responses remain auditable, traceable, and grounded in actual source material. like a research team that never stops investigating until they have the complete picture. This agentic approach represents a significant step toward more dependable AI systems. The new feature is now available as a public preview in Google's Gemini Enterprise Agent platform, ready for organizations that need thorough, multi-source information retrieval. I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. Breathe gently and let that sink in. This difference between a detective looking at only the first clue versus a thorough investigative team that follows each thread to its conclusion. Those islands of data you've encountered, where related information sits scattered across different systems, you understand this frustration deeply. The partial answers, the not found responses, when you know the information exists somewhere in your organization. Now let's step back and look at the bigger picture, at how this shift toward foundation models is reshaping the very way organizations approach machine learning problems. Picture the evolution of enterprise AI as resembling the transformation of a craftsman's workshop, where individual specialized tools are giving way to sophisticated, adaptable systems that can handle multiple tasks with shared intelligence. This shift toward foundation models represents more than just a technical upgrade. It's reshaping how organizations approach machine learning problems across domains like financial transactions, enterprise search, and structured data analysis, the very applications we've been exploring throughout this discussion. The traditional approach to enterprise AI involved building task-specific models for each business problem, much like having a separate key for every door in a large office building. Teams would architect fraud detection systems from scratch, build separate models for customer recommendations, and create distinct solutions for document search, each one requiring its own data pipeline, training infrastructure, and maintenance overhead. This specialized approach worked well for individual problems, but created what researchers call the training data bottleneck, where each new task required collecting substantial labeled examples and expert feature engineering. A credit scoring model needed thousands of loan outcomes. A customer churn predictor required extensive historical behavior data, and each system remained isolated from the insights that other models might provide. Foundation models emerged from a different philosophy entirely, training large neural networks on vast amounts of general data to learn broad representations that can be adapted to specific tasks. Think of this like teaching someone to become a skilled translator by first giving them a deep education in literature, history, and culture, rather than just memorizing phrase books for individual languages. The transformer architecture that powers these foundation models excels at finding patterns in sequential data, whether that's words in a sentence, transactions in a financial history, or events in an enterprise workflow. The attention mechanism allows the model to focus on relevant information across long sequences, like a detective who can simultaneously consider multiple clues and their relationships when solving a complex case. For enterprise applications, this architectural foundation enables capabilities we've seen throughout our discussion tonight. Agent logic systems that can reason across multiple data sources, transaction foundation models that understand financial behavior in context, and agentic RAG systems that can orchestrate complex information retrieval tasks. The same underlying transformer architecture adapts to handle structured tabular data, unstructured documents, and hybrid reasoning tasks. These foundation models, as they came to be called, work more like a Swiss Army knife that's been engineered by a master craftsman. The base model learns general patterns about language, images, or whatever domain it's trained on, developing a rich internal understanding that can then be specialized for specific tasks through a process called fine-tuning, which requires much less data and compute than training from scratch. Think of fine-tuning like teaching a skilled carpenter to work with a new type of wood, They already understand grain patterns, joint construction, tool handling, and wood behavior in general. When they encounter bamboo for the first time, they don't need to relearn carpentry from scratch. They just need to understand how bamboo differs from oak or pine, then apply their existing expertise with those adjustments in mind. The economic implications of this shift are profound, like the difference between maintaining a fleet of specialized vehicles versus having a few versatile trucks that can be configured for different jobs. Instead of training 50 task-specific models, an organization might train or license one foundation model, then fine-tune it for their 50 use cases, dramatically reducing the compute costs, data requirements, and engineering overhead. Foundation models also solve the cold start problem that plagued task-specific approaches. When you wanted to build a model for a new task where you had limited training data, you'd often struggle to achieve good performance. It's like trying to learn a new language with only a pocket dictionary. But with a foundation model, you start with something that already understands language structure, context, and meaning. Then teach it the specific vocabulary and patterns of your domain. The technical architecture of foundation models reflects this versatility through their sheer scale and generality. Where a task-specific model might have millions of parameters tuned for one narrow job, foundation models typically have billions or even trillions of parameters, creating a rich representational space that can capture the complexity of general intelligence, rather than just pattern matching for a single task. This representational richness works like having a detailed topographic map of an entire continent, rather than a street map of just your neighborhood. When you need to navigate somewhere new, you don't need to survey the terrain from scratch. You can zoom into the relevant section of your comprehensive map and find the paths that connect to where you want to go. The training process for foundation models reflects this generality as well. Instead of curating a specific dataset for a narrow task, foundation model training involves exposing the model to massive, diverse datasets that represent the breadth of human knowledge and communication. A language foundation model might train on books, articles, websites, conversations, technical documentation, creative writing, and scientific papers all mixed together. This diverse training creates what researchers call emergent capabilities, behaviors and skills that weren't explicitly programmed but arise naturally from the model's exposure to patterns across many domains. It's like how a well-traveled chef doesn't just know individual recipes, but develops an intuitive understanding of flavor combinations, cooking techniques, and ingredient relationships that lets them improvise and adapt in ways that weren't part of their formal training. The fine-tuning process then acts like a focused apprenticeship, where the foundation model's general capabilities get channeled toward specific objectives. This might involve training on task-specific examples, adjusting the model's responses based on human feedback, or constraining its outputs to match particular formats or styles required by the application. One of the most compelling advantages of foundation models becomes apparent when you need to deploy multiple related tasks. It's like having a master key that can be slightly modified to open different locks in the same building, rather than crafting completely separate keys for each door. A single language foundation model can be fine-tuned for translation, summarization, question answering, code generation, and creative writing, sharing the computational investment across all these applications. The maintenance story also transforms dramatically with foundation models. Instead of monitoring and updating dozens of separate task-specific models, teams can focus their efforts on maintaining and improving the core foundation model, with those improvements automatically benefiting all the downstream applications. It's like upgrading the engine in a vehicle platform that's used across multiple car models. Every vehicle in the lineup gets better performance from that single improvement. However, foundation models aren't universally superior to task-specific approaches, and the choice between them involves real trade-offs. Foundation models are like powerful, general-purpose machines that require significant resources to run. They need more memory, more compute power, and often have higher latency than a lean, specialized model designed for just one task.
Think of it like the difference between an industrial 3D printer that can work with dozens of materials and create complex geometries, versus a simple injection molding machine designed to produce one specific plastic part. The 3D printer offers incredible flexibility, but if you need to produce millions of identical bottle caps, the injection molding setup will be faster, cheaper per unit, and more reliable. Task-specific models also offer advantages in interpretability and control. When a model is designed for one narrow job, it's often easier to understand why it makes particular decisions and to constrain its behavior within acceptable bounds. Foundation models, with their vast parameter spaces and emergent capabilities, can sometimes behave in unexpected ways that are harder to predict or explain. The security and privacy implications differ as well. A task-specific model, trained only on your customer support tickets, poses a different risk profile than a foundation model that's absorbed patterns from across the internet. It's like the difference between a filing cabinet that contains only your company's documents versus a vast library that includes sensitive information from many sources. The potential for unintended information leakage varies significantly. In practice, many organizations are finding that the optimal approach involves a hybrid strategy, like a workshop that has both the versatile multi-tool and a few essential specialized implements. They might use foundation models for most applications where flexibility and rapid deployment matter, while maintaining task-specific models for critical applications where performance, latency, or interpretability requirements are paramount. The economic forces driving adoption of foundation models are particularly strong for organizations that need to solve many related problems. A technology company building various AI features across their product suite finds it much more cost-effective to fine-tune one foundation model for multiple applications than to build separate models for each feature. The development time shrinks from months to weeks, and the maintenance burden scales much more favorably. As you settle into sleep tonight, consider how this shift from specialized to general-purpose models mirrors patterns we've seen across many technologies. The same economic pressures that led to general-purpose computers replacing specialized calculators or smartphones consolidating dozens of single-purpose devices are now reshaping how we think about machine intelligence. The workshop of the future will likely have fewer tools, but each one will be far more capable and adaptable than what we use today. Take a quiet moment to absorb this transformation from separate keys for every door to something more adaptable and shared. You've lived through this evolution, building those task-specific models, creating distinct solutions for fraud detection and customer recommendations, each one requiring its own careful maintenance. You know the weight of that overhead. Now, let's turn to something quite specific and revolutionary, a foundation model called NEXUS that's designed to understand the structured data that lives in your spreadsheets and databases. Think of your enterprise data as a vast library of spreadsheets, each one holding pieces of the puzzle that could transform your business decisions. And tonight, we're going to explore how a new kind of foundation model called NEXUS is changing the way we make predictions from all that structured information sitting in your databases, CRM systems, and ERP platforms. Most of the valuable data in your organization lives in tables, much like the organized rows and columns of a well-maintained garden, where each plant has its designated spot, its measured nutrients, its recorded growth patterns, and NEXUS represents the first foundation model built specifically to understand this tabular landscape, rather than forcing it through tools designed for text. Traditional machine learning approaches to tabular data have always felt like asking a team of craftsmen to hand forge each tool they need before they can even begin their real work, typically requiring 3 to 6 months of feature engineering, model training, and deployment just to tackle a single prediction task. Large language models, while revolutionary for text, struggle with structured data because they lose numerical precision during tokenization. Like trying to measure the exact temperature of water by describing it in words rather than using a thermometer, leading to inconsistent results and requiring complex guardrails to maintain accuracy. NEXUS takes a fundamentally different approach, arriving pre-trained on billions of real-world prediction tasks across structured datasets, so it already knows how to find signal in your data without requiring months of preparation. The architecture maintains consistency in predictions rather than the probabilistic variations common in language generation, meaning that identical inputs produce identical outputs each time, like a precision scale that always shows the same weight for the same object, though the underlying model still uses probabilistic computations during its internal reasoning process. One of NEXUS's key innovations is what's called permutation invariance, recognizing that changing the order of columns in your table doesn't change the underlying meaning, much like how rearranging the instruments in an orchestra doesn't change the musical relationships between the notes they play. The model can process billions of rows without truncation or sampling, handling massive datasets in their entirety rather than working with approximations. And it performs what the developers call cross-schema reasoning, automatically connecting related data across disparate tables. Perhaps most practically, NEXUS includes autonomous data cleaning capabilities, resolving incomplete entries, and still making predictions even when some data points are missing, like a skilled chef who can still prepare a delicious meal even when a few ingredients from the recipe aren't available. When you deploy NEXUS on Amazon SageMaker, it runs on a dedicated single-tenant network-isolated GPU instance, specifically an ML.P5EN.48X large instance equipped with 8 NVIDIA H200 GPUs, providing the computational horsepower needed for enterprise-scale tabular reasoning. The workflow feels familiar to data scientists because the fundamental Python SDK provides a scikit-learn-compatible API with NEXUS classifier and NEXUS regressor estimators, so you can call the same fit and predict methods you're already accustomed to using. Your data stays within your AWS environment throughout the entire process, like keeping sensitive documents in your own locked filing cabinet, rather than sending them to an external office, with the endpoint remaining network isolated and single-tenant for enterprise security requirements. The model comes in several variants, including a base model pre-trained on over 10 billion tabular rows, plus industry-specific versions tailored for finance, healthcare, and manufacturing, each one fine-tuned to understand the particular patterns and relationships common in those domains. In financial services, NEXUS can analyze transaction patterns across millions of accounts for fraud detection, process loan portfolios with automated feature extraction for credit risk modeling, and extract structured insights from unstructured regulatory filings for compliance purposes. Healthcare applications include clinical trial matching by identifying eligible patients across electronic health record systems, drug discovery through analysis of biological assay data for compound screening, and patient risk stratification by predicting readmission risks using ICU time series data. Manufacturing and supply chain use cases span predictive maintenance by forecasting equipment failures from sensor data, demand forecasting to anticipate inventory needs across global distribution networks, and supplier risk analysis using procurement history to evaluate vendor reliability. In retail and e-commerce, the model excels at churn prediction by identifying at-risk customers through purchase history and browsing behavior, dynamic pricing optimization based on competitor data and inventory levels, and cart abandonment analysis to understand customer decision points. The integration with Amazon SageMaker provides managed infrastructure that scales automatically to handle petabyte-scale datasets, like having a construction crew that can instantly expand your workshop to accommodate any size project without you needing to manage the logistics of hiring, equipment, or space planning. Compliance requirements are handled by default, meeting GDPR, HIPAA, and SOC2 standards, while the platform supports multiplex operations, allowing multiple fit and predict operations on a single endpoint, rather than requiring dedicated resources for each use case. The strategic partnership between Fundamental and AWS enables native integration through AWS Marketplace, secure infrastructure deployment on AWS's compliant cloud environment, and dedicated solutions architects for implementation guidance, creating a complete ecosystem for enterprise tabular AI. Getting started involves navigating to Amazon SageMaker Jumpstart, searching for Fundamental NEXUS, and choosing the variant that best matches your industry and use case. Pre-built containers and example notebooks provide guided deployment processes, allowing teams to begin experimenting with tabular foundation models within their existing AWS infrastructure. This represents a fundamental shift in how we approach structured data prediction, moving from months-long custom model development cycles to days-long deployment of pre-trained foundation models that already understand the deep patterns hidden within tabular data across industries and applications. As you drift towards sleep tonight, consider how this convergence of foundation model capabilities with enterprise tabular data might transform the prediction tasks in your own domain, turning those spreadsheets and databases from static repositories into dynamic sources of actionable intelligence, ready to reveal their insights with the same ease that language models now generate text. Rest with this understanding of NEXUS and how it's changing the way we work with the tabular data that holds so much of your organization's valuable information. No more hand-forging each tool before beginning the real work. No more months of feature engineering for every single prediction task. You can feel the relief in that, can't you? Now, let's journey back to 2020 to understand how researchers first began combining the fluid generation of language models with the explicit knowledge contained in external documents. Back in 2020, when large pre-trained language models like BERT and GPT were showing impressive abilities to store factual knowledge within their parameters, researchers at Facebook AI Research and University College London were tackling a fundamental limitation of these purely parametric approaches. They couldn't easily update their knowledge or explain their reasoning, and they sometimes generated plausible-sounding but incorrect information, like a scholar confidently citing a non-existent reference. The team, led by Patrick Lewis and colleagues, introduced Retrieval Augmented Generation, or RAG, which combined the fluid text generation capabilities of pre-trained sequence-to-sequence models with the explicit, updatable knowledge contained in external documents. The RAG architecture worked like a research assistant with access to both memorized knowledge and a well-organized library, combining what researchers called parametric memory, the knowledge encoded in neural network weights, with non-parametric memory in the form of a searchable index of Wikipedia articles. The system used a pre-trained BART model as its generator component, and dense passage retrieval, or DPR, as its retrieval component, with Wikipedia split into 21 million chunks of roughly 100 words each, creating a vast external knowledge base that could be searched and referenced during generation. Lewis and his colleagues proposed two distinct variants of their approach, each handling the integration of retrieved documents differently, much like two different strategies for consulting reference materials while writing. RAG sequence assumed that a single retrieved document would inform the generation of an entire output sequence, treating document selection as a single decision that would guide all subsequent text generation, while RAG token allowed the model to potentially consult different documents for each generated token, enabling more flexible knowledge integration throughout the generation process. The training process required careful orchestration of both the retrieval and generation components, resembling a conductor synchronizing an orchestra where different sections must play in harmony. Rather than providing explicit supervision about which documents should be retrieved for each query, the researchers trained the system end-to-end by minimizing the negative log likelihood of target outputs, allowing the model to learn implicitly which documents were most useful for generating correct answers, while keeping the document encoder frozen and only fine-tuning the query encoder and BART generator. For open domain question answering evaluation, the researchers tested RAG on 4 established datasets: natural questions, trivia QA, web questions, and curated TREC, treating questions and answers as input-output pairs and comparing against both extractive approaches that selected spans from retrieved documents and closed-book approaches that relied purely on parametric knowledge, like a student taking a test with or without access to textbooks. RAG achieved state-of-the-art results across all datasets, with particularly impressive performance on natural questions, where it scored 44.5% exact match, substantially outperforming previous approaches, and demonstrating that generative models could exceed the performance of traditional extractive question answering systems. Beyond traditional question answering, the team evaluated RAG's generation capabilities on MS Marco, treating it as an open-domain abstractive question answering task by discarding the provided gold passages and relying only on Wikipedia retrieval, much like a researcher answering questions armed only with an encyclopedia, rather than specifically curated source materials. RAG sequence outperformed BART by 2.6 blue points and 2.6 rouge L points, approaching the performance of systems that had access to gold passages specifically selected to contain the information needed for correct answers. To test knowledge-intensive generation in a non-question answering setting, Lewis and colleagues introduced the novel task of generating Jeopardy questions from answer entities, requiring the model to produce precise, factual statements that would lead contestants to guess the given answer, like crafting clues for an elaborate word game where accuracy and specificity were paramount. On this challenging task, RAG token achieved 17.3 blue 1, compared to BART's 15.1, with human evaluators finding RAG generations more factual in 42.7% of pairwise comparisons, while finding BART more factual in only 7.1% of cases. The FEVER, fact verification task, provided an opportunity to test RAG's classification abilities, requiring the system to determine whether natural language claims were supported, refuted, or unverifiable based on Wikipedia evidence, functioning like a fact-checker with access to a comprehensive reference collection, but without explicit guidance about which sources to consult. Despite not using supervision on retrieved evidence, unlike most competing approaches, RAG achieved accuracy within 4.3% of state-of-the-art pipeline systems on the three-way classification task and within 2.7% on two-way classification, demonstrating competitive performance without the engineering complexity of specialized architectures. Analysis of RAG tokens' behavior during Jeopardy question generation revealed fascinating dynamics in how the model balanced parametric and non-parametric knowledge, resembling a jazz musician who starts with sheet music but improvises as the melody develops. When generating "The Sun Also Rises" in a question about Hemingway, the model initially relied heavily on a specific retrieved document containing that title, but after generating the first token "sun," the document posterior flattened as BART's internal knowledge proved sufficient to complete the familiar phrase.
The researchers demonstrated RAG's ability to update its knowledge by simply swapping document indices, testing this capability by building indices from Wikipedia dumps from December 2016 and December 2018, and querying about world leaders who had changed between these dates, like updating a reference desk by replacing old almanacs with current editions. RAG answered 70% of questions correctly when the index matched the time period, but only 12% or 4% with mismatched indices, proving that knowledge updates could be accomplished without retraining the entire model. Ablation studies revealed the importance of learned retrieval over fixed approaches, with RAG outperforming systems using traditional BM25 keyword-based retrieval on most tasks. Though BM25 performed better on Fever, where entity-centric claims benefited from word overlap matching, much like different filing systems serving different organizational needs. The researchers also found that retrieving more documents at test time generally improved performance for RAG sequence, but showed diminishing returns for RAG token after 10 documents, suggesting optimal resource allocation strategies for each variant. Human evaluation of generation quality revealed that RAG models produced more diverse outputs than BART, without requiring specialized diversity-promoting decoding techniques, calculating higher ratios of distinct trigrams to total trigrams across generation tasks, like a well-read author drawing from a broader vocabulary than one with limited reading experience. This diversity came alongside improved factuality, suggesting that access to external knowledge encouraged both accuracy and linguistic variety in generated text. The work positioned RAG within a broader landscape of memory-augmented architectures, distinguishing itself from previous approaches by using raw text rather than learned embeddings as its external memory, making the system's knowledge both human-readable for interpretability and human-writable for updates, like maintaining a traditional card catalog alongside a digital database. This design choice enabled the straightforward knowledge updating demonstrated with the Wikipedia index swapping experiment. RAG's architectural innovations built upon earlier successes with retrieval in individual NLP tasks, unifying previous task-specific advances into a general-purpose framework that could be fine-tuned across multiple knowledge-intensive applications, resembling a Swiss Army knife that consolidated specialized tools into a single, versatile instrument. The combination of BART's generation capabilities with DPR's retrieval mechanism provided a foundation that proved effective across question answering, fact verification, and open-ended generation tasks. The 2020 research established retrieval-augmented generation as a significant paradigm shift in how language models could access and utilize knowledge, moving beyond the limitations of purely parametric approaches toward hybrid systems that combined learned representations with explicit, searchable information sources, like bridging the gap between intuitive knowledge and documented facts in human reasoning. This work laid important groundwork for subsequent developments in retrieval-augmented language models that would become increasingly prominent in the years that followed, demonstrating that external knowledge integration could enhance both the accuracy and reliability of neural text generation across diverse applications. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour. Let this settle gently. This story of how researchers first solved the problem of models that couldn't update their knowledge or explain their reasoning. That research assistant with access to both memorized knowledge and a well-organized library, combining what lived in the neural network with what could be searched and retrieved. You can see how this foundation connects to everything we've been discussing. Now, let's explore how other researchers discovered something troubling about the attention mechanisms that seemed so promising. Back in 2021, researchers at Shanghai Jiao Tong University and Soochow University
took a hard look at what seemed to be an insurmountable problem with transformer-based language models like BERT and Roberta. Observing that these massive pre-trained systems were succumbing to overfitting despite their impressive capabilities. Like a master chef whose elaborate dish suffers because too many ingredients compete for attention, self-attention networks were experiencing what the authors called severe co-adaptation between attention elements, where parts of the model became overly dependent on each other in ways that hurt generalization. The core insight driving this work emerged from several troubling discoveries about self-attention mechanisms that had accumulated in the research literature by 2021, including evidence that fixed Gaussian or even random attention matrices could sometimes rival standard self-attention, and that deep self-attention networks suffered from rank collapse as layers deepened, like sediment gradually choking a riverbed until water can no longer flow freely. The researchers attributed these problems to information diffusion, where input vectors progressively assimilated through continuous self-attention operations until the model lost its ability to maintain useful distinctions between different types of information. While dropout had long served as the standard remedy for overfitting, existing approaches fell short when applied to self-attention architectures, with random-based methods requiring exhaustive grid searches, knowledge-based methods demanding costly prior information, and search-based methods consuming enormous computational resources, while still producing static, sample-independent patterns. The authors proposed attend-out, a novel dropout method that dynamically generates attention-specific dropout patterns for each layer and each sample through an end-to-end learning process, functioning like an intelligent conductor who adjusts the orchestra's volume and timing in real time based on the acoustic properties of each concert hall and the specific piece being performed. Attend-out's architecture centered on a three-way competition between identical models playing different roles, with the defender receiving standard dropout, the attacker receiving additional dropout patterns from a generator network, and the generator learning to produce dropout masks that would help the attacker outperform the defender. The generator itself was a streamlined self-attention model that exported only attention scores, used single-head attention with shared parameters across layers, and excluded feed-forward components entirely, operating like a specialized referee who watches the main game while learning the optimal rules to create the most competitive and robust players. The training process unfolded through policy gradient optimization, where after every T steps, the researchers evaluated both defender and attacker on validation samples, rewarding the generator positively when the attacker achieved higher scores and punishing it when the defender won. This created a dynamic learning system where the generator learned to produce increasingly sophisticated dropout patterns by observing the performance differences between the two competing models, with the independence assumption allowing them to treat each dropout decision as separate to make the massive n by L squared search space computationally tractable, functioning like a chess master who learns strategy by analyzing thousands of games between opponents of varying skill levels. The experimental evaluation in 2021 demonstrated attend-out's effectiveness across an extensive range of natural language processing tasks, including 5 GLUE benchmark tasks, SST2, MRPC, QNLI, MNLI, and COLA, document classification on IMDb, named entity recognition on CoNLL 2003, part of speech tagging on Penn Treebank, and multiple choice question answering on SWAG. The researchers applied their method to both BERT and Roberta models, maintaining identical hyperparameters between baseline and attend-out variants to ensure fair comparison, with results that sparkled like gems across the evaluation landscape, showing consistent improvements even on datasets where the base models already achieved strong performance. The results revealed attend-out's particular strength on smaller datasets prone to overfitting, where it achieved remarkable gains, such as 12.1% improvement over BERT on COLA and 1.7% over BERT on MRPC, while still producing meaningful improvements on larger, more stable datasets like MNLI, with 1.4% gains over Roberta. These improvements extended across diverse task types, including 1.1% gains over BERT on PTB part-of-speech tagging, though the method showed more modest effects on some tasks, like SWAG, with only 0.4% improvement over Roberta, creating a performance profile that rose and fell like mountain peaks of varying heights across the experimental landscape. Analysis of the learned dropout patterns revealed fascinating task-specific behaviors, with lower attention layers consistently receiving higher dropout probabilities across different datasets, and the dropout probabilities evolving dynamically throughout training in ways that differed markedly between tasks. On COLA, which contained only 8,500 training samples and was particularly susceptible to overfitting, the system learned to apply dropout probabilities approaching 0.9 in the final training period, while larger datasets exhibited more moderate and gradually changing patterns, resembling how a thermostat automatically adjusts heating based on both the current temperature and the thermal properties of the specific room it's monitoring. The convergence analysis showed that while attend-out enhanced models often started slower due to the stronger dropout mechanism, they typically overtook their standard counterparts by the second epoch and maintained more stable performance throughout training. On MNLI, for example, standard Roberta achieved better results in the first 2 epochs, but dropped in performance during the final epoch, while the attend-out version showed steady improvement across all 3 epochs, demonstrating the regularization benefits, like a marathon runner who starts conservatively but maintains energy reserves for a strong finishing sprint. Ablation studies confirmed attend-out superiority over simpler alternatives, with vanilla dropout showing inconsistent results and actually performing 1.9% below Roberta on COLA, while attend-out maintained advantages of 4.1%, 1.0%, and 1.0% over vanilla dropout on COLA, QNLI, and MNLI, respectively. The comparison with layer drop, which removes entire encoder blocks, showed that attention-specific dropout proved more effective than broader architectural modifications, while a simplified scheduler that approximated attend-out's learned patterns using piecewise linear Bernoulli dropout achieved surprisingly good results, validating the correctness of the dynamic patterns like an apprentice successfully copying the master's technique with simpler tools. The computational cost of attend-out represented a significant consideration, requiring roughly twice the GPU memory and training time compared to single model approaches due to the need for 2 identical models plus the generator network. The authors position this as a middle ground between simple random dropout and computationally intensive neural architecture search methods, with the generator network requiring approximately 1/3 the size of the main models, creating a resource profile that balanced effectiveness against efficiency, like a luxury car that consumes more fuel but delivers substantially better performance and reliability. The method's applicability extended to both fine-tuning and pre-training phases of language model development, though the authors noted that pre-training applications would be particularly expensive and less critical, since large-scale pre-training with modest epochs was generally less susceptible to overfitting. Their focus on fine-tuning addressed what they considered the most delicate part of the training process, where task-specific data limitations made models most vulnerable to the co-adaptation problems that attend-out was designed to solve, targeting their intervention like a surgeon who focuses on the most critical and vulnerable part of a complex operation. The theoretical foundation of attend-out rested on the observation that traditional dropout methods applied to attention mechanisms were fundamentally limited by their static, sample-independent nature, failing to account for the dynamic relationships that made self-attention powerful in the first place. By leveraging self-attention itself to generate dropout patterns, the method created a self-improving system where the attention mechanism learned to regulate its own complexity based on the specific requirements of each input sample and training context, functioning like an ecosystem where predators and prey naturally balance each other to maintain optimal population dynamics. The paper's contribution to the field in 2021 represented a significant advance in understanding how to effectively regularize large-scale pre-trained language models, demonstrating that the attention mechanism could be turned inward to solve its own overfitting problems through intelligent adaptive dropout. The work challenged the prevailing assumption that dropout patterns should be fixed and random, instead showing that dynamic, learned patterns could provide substantial improvements across diverse natural language processing tasks, opening new directions for research into self-regulating neural architectures like a key that unlocks a previously sealed door to a room full of unexplored possibilities. Looking back from our current perspective in 2026, this 2021 work anticipated many of the adaptive training techniques that have since become standard in large language model development, particularly the insight that models could learn to regulate their own training dynamics through meta-learning approaches. While the specific three-network architecture of Attendout may seem elaborate compared to some later innovations, the core principle of using attention mechanisms to guide their own regularization established an important precedent for self-modifying training procedures, standing like a lighthouse that helped guide subsequent research toward more sophisticated adaptive learning systems. Breathe slowly and let go of the technical details about co-adaptation and rank collapse. What matters is that researchers found ways to improve these systems, just as they found solutions to the overfitting problems that seemed insurmountable. You don't need to carry the complexity, only the understanding that each challenge led to better approaches. Now, let's return to that pivotal moment in 2020 when OpenAI showed us something remarkable about how models could learn from just a few examples. Back in 2020, OpenAI published groundbreaking research that fundamentally shifted how we think about training and using large language models. Introducing GPT-3, a 175 billion parameter autoregressive language model that demonstrated remarkable abilities to perform tasks without any training updates. Like a master chef who can prepare any dish simply by observing a few examples, rather than attending culinary school, GPT-3 showed that scaling up language models dramatically improved their capacity for few-shot learning, performing new tasks based solely on a handful of demonstrations provided in the text input, without any gradient updates or fine-tuning. The researchers challenged the prevailing wisdom that effective language models required extensive task-specific fine-tuning on thousands of labeled examples, which had become the dominant paradigm following earlier successes with models like BERT and GPT-2. This traditional approach was like requiring a translator to undergo months of specialized training for each new language pair, creating practical limitations since collecting large supervised datasets for every possible language task was often difficult or impossible, and the resulting models could suffer from overfitting to narrow training distributions. GPT-3's architecture was fundamentally similar to GPT-2, using the same transformer design with modified initialization, pre-normalization, and reversible tokenization, but incorporated alternating dense and locally banded sparse attention patterns in the transformer layers. The team trained 8 different model sizes, ranging from 125 million to 175 billion parameters, the largest being 10 times bigger than any previous non-sparse language model, like constructing a series of increasingly powerful telescopes to observe how performance scaled with computational capacity. Training data for GPT-3 consisted of a carefully curated mixture, totaling roughly 300 billion tokens, with the largest component being filtered common crawl data, 45 terabytes compressed, filtered down to 570 gigabytes, supplemented by WebText 2 books corpora, and English Wikipedia. The researchers deliberately sampled higher quality datasets more frequently during training, rather than sampling proportionally by size, accepting minor overfitting in exchange for better training data quality, though they acknowledged that a filtering bug allowed some test set contamination that they couldn't address due to retraining costs. The evaluation framework distinguished 4 different learning paradigms along a spectrum of task-specific data requirements: traditional fine-tuning with thousands of examples, few-shot learning with 10 to 100 demonstrations, one-shot learning with a single example plus instructions, and zero-shot learning with only natural language instructions. Like a student taking exams under increasingly challenging conditions, from open book with study guides to completely closed book, these settings tested the model's ability to adapt to new tasks with progressively less contextual support. On language modeling benchmarks, GPT-3 achieved substantial improvements over previous state-of-the-art results, setting a new record on PenTreeBank with a perplexity of 20.50 compared to the previous best of 35.8. The Lambda dataset, which tests long-range dependency modeling by requiring prediction of sentence final words needing paragraph context, saw particularly dramatic gains. GPT-3 achieved 76% accuracy in zero-shot setting and 86.4% in few-shot, compared to previous state-of-the-art of 68%, like a detective who could solve increasingly complex cases by gathering more contextual clues. Few-shot learning performance showed remarkable scaling properties, with larger models demonstrating increasingly steep in-context learning curves, as they were provided with more demonstration examples within their context window. The researchers found that while zero-shot performance improved steadily with model size, few-shot performance increased much more rapidly, suggesting that larger models became significantly more proficient at extracting patterns from contextual demonstrations, like musicians who could more quickly pick up new songs by hearing just a few bars. On closed-book question-answering tasks, where models must rely entirely on knowledge stored in their parameters, rather than accessing external sources, GPT-3 showed impressive capabilities across natural questions, web questions, and Trivia QA datasets. For Trivia QA specifically, the model achieved 64.3% accuracy in zero-shot, 68.0% in one-shot, and 71.2% in few-shot settings, with the latter matching or exceeding the performance of RAG, the previous state-of-the-art fine-tuned open-domain model, like a walking encyclopedia that could answer increasingly difficult questions as it was given more context about the desired response format. Translation capabilities emerged organically from GPT-3's training, with the model showing competent performance across multiple language pairs, despite not being explicitly trained as a translation system. The few-shot setting allowed the model to understand translation tasks simply from seeing input-output pairs in context, demonstrating the flexibility of the in-context learning approach compared to traditional task-specific fine-tuning methods, though performance varied significantly across different language pairs and was generally below specialized translation models. On the SuperGLUE benchmark suite, a collection of challenging natural language understanding tasks, GPT-3 achieved competitive but mixed results, with some tasks showing strong performance approaching fine-tuned baselines, while others remained challenging. The model particularly struggled with certain natural language inference tasks and some reading comprehension datasets like race, revealing that even at GPT-3's scale, few-shot learning had clear limitations, like a versatile athlete who excelled at many sports but still had specific weaknesses requiring targeted training. Perhaps most remarkably, GPT-3 demonstrated proficiency at novel tasks designed to test rapid adaptation and on-the-fly reasoning, including unscrambling words, performing arithmetic, and using new words correctly after seeing them defined only once. The model could also generate synthetic news articles that human evaluators found difficult to distinguish from human-written content, suggesting that the few-shot learning capabilities extended beyond pattern matching
to more creative and generative applications, like an improvisation actor who could seamlessly adopt any role with minimal direction. The research revealed that model scaling continued to follow predictable power law relationships even when extended by 2 additional orders of magnitude beyond previous studies, with validation loss decreasing smoothly as computational resources increased. Cross-entropy improvements consistently translated into better performance across diverse natural language tasks, contradicting concerns that larger models might only capture spurious details rather than developing genuine language understanding capabilities. Like a growing tree whose increased size directly correlates with its ability to weather various environmental challenges. Systematic analysis of data contamination, where test set content might have appeared in the training data scraped from the web, revealed minimal impact on most benchmark results, though the researchers identified several data sets where contamination could have inflated performance measures. They developed tools to detect and quantify such contamination, marking affected results appropriately, recognizing that this issue would become increasingly important as models trained on large web corpora became more common and capable of memoization.
The study broader impact analysis acknowledged significant concerns about potential misuse, bias, and fairness issues inherent in large language models trained on web data, while also noting the substantial computational resources required for training. GPT-3 consumed roughly 50 petaflop-second days of compute during pre-training. These considerations highlighted the need for careful deployment and ongoing research into the societal implications of increasingly capable language models, like wielding a powerful tool that required both technical skill and ethical responsibility to use appropriately. GPT-3's introduction marked a pivotal moment in natural language processing, demonstrating that the combination of scale and few-shot learning could approach or sometimes exceed the performance of task-specific fine-tuned models across a broad range of applications. The research established few-shot learning as a viable alternative to traditional fine-tuning paradigms, opening new research directions while highlighting both the tremendous potential and important limitations of very large language models, like discovering a new continent that promised great opportunities but required careful exploration to map its boundaries and navigate its challenges. Rest here with this beautiful idea of few-shot learning, of models that can perform new tasks based on just a handful of demonstrations, like that master chef who can prepare any dish simply by observing. This was another crucial step toward the foundation model approaches that are transforming your field. Now, for our final exploration, let's go back to 2018 to BERT and understand how bidirectional understanding changed everything about language processing. Back in 2018, Google researchers introduced BERT, which stands for Bidirectional Encoder Representations from Transformers, marking a pivotal shift in how we approach language understanding tasks. Like a translator who can see an entire sentence before choosing the meaning of each word, BERT was designed to look at text from both directions simultaneously, rather than processing it only from left to right, as previous models had done. The key innovation lay in its pre-training approach, which used a masked language model objective, where random words were hidden, and the model had to predict them based on surrounding context, along with a next sentence prediction task that helped it understand relationships between sentence pairs. The researchers addressed a fundamental limitation in existing language models, which could only process text unidirectionally, like reading a book with one eye covered, missing crucial context that comes after each word. Previous approaches, like OpenAI's GPT, used left-to-right architectures where each token could only attend to previous tokens, creating what the authors argued were suboptimal representations, especially for tasks requiring understanding of full sentence context. BERT's bidirectional approach allowed the model to incorporate both left and right context at every layer, enabling richer understanding of language structure and meaning. The model architecture built upon the transformer encoder, functioning like a sophisticated assembly line, where each layer processes and refines the understanding of text through self-attention mechanisms. The researchers created two model sizes: BERT base with 12 layers, 768 hidden units, and 110 million parameters, designed to match OpenAI GPT size for comparison purposes, and BERT large with 24 layers, 1024 hidden units, and 340 million parameters. The critical difference was that BERT's transformer used bidirectional self-attention, while GPT's version used constrained self-attention limited to left context only. BERT's input representation system worked like a sophisticated filing system, capable of handling both single sentences and sentence pairs within a unified framework. The model used word piece embeddings with a 30,000 token vocabulary, beginning every sequence with a special classification token called SCLS, and separating sentence pairs with a SEP token. For each token, the input representation combined three types of embeddings: token embeddings, what the word is; segment embeddings, which sentence it belongs to; and position embeddings, where it sits in the sequence. The pre-training process employed two innovative tasks that taught BERT to understand language in unprecedented ways, like a student learning through carefully designed exercises. The masked language model task randomly masked 15% of input tokens, with 80% replaced by masked tokens, 10% replaced by random tokens, and 10% left unchanged, forcing the model to predict original tokens based on bidirectional context. The next sentence prediction task presented the model with sentence pairs where 50% were actual consecutive sentences labeled is next, and 50% were random pairs labeled not next, teaching it to understand sentence relationships. Pre-training data came from two massive text sources: the books corpus containing 800 million words and English Wikipedia with 2.5 billion words, creating a foundation like a vast library of human knowledge. The researchers emphasized the importance of using document-level corpora rather than shuffled sentence collections, as this allowed extraction of long contiguous sequences, essential for understanding context and relationships between sentences. This careful curation of training data provided the rich linguistic patterns necessary for BERT's bidirectional understanding capabilities. Fine-tuning BERT for downstream tasks proved remarkably straightforward, functioning like a master key that could be adapted to open many different locks with minimal modification. The self-attention mechanism allowed BERT to handle various task types, single text or text pairs, by simply adjusting inputs and outputs while fine-tuning all parameters end-to-end. For classification tasks, the model used the CLS token representation, while for token-level tasks like question answering, it used individual token representations, fed through task-specific output layers. The experimental results demonstrated BERT's superiority across 11 natural language processing tasks, with performance improvements like a rising tide that lifted all benchmarks simultaneously. On the GLUE benchmark, BERT achieved an 80.5% score, with a 7.7 percentage point absolute improvement over previous state-of-the-art systems, while on multi-NLI, it reached 86.7% accuracy with a 4.6 point improvement. Both BERT base and BERT large substantially outperformed existing systems across all tasks, with BERT base showing the impact of bidirectionality by outperforming the architecturally similar but unidirectional OpenAI GPT. On the Stanford Question Answering Dataset, Squad V1.1, BERT's approach treated question answering like a precision search operation, representing questions and passages as single sequences and introducing start and end vectors to identify answer spans. The model computed probabilities for each word being the start or end of an answer through dot products and softmax operations, selecting the highest scoring valid span as its prediction. BERT achieved a 93.2 F1 score on Squad V1.1,
representing a 1.5-point improvement over previous best systems, with the single model outperforming even ensemble approaches. The Squad v2.0 evaluation presented a more challenging scenario, where some questions had no answers in the provided text, like a detective investigating cases that might have no solution. BERT addressed this by treating unanswerable questions as having answer spans at the CLS token position, comparing no-answer scores against best non-null spans using a threshold optimized on development data. This approach yielded an 83.1 F1 score, representing a substantial 5.1-point improvement over previous systems without using additional training data beyond the core pre-training corpus. Testing on the SWAG dataset, which evaluated common sense reasoning through sentence completion, BERT operated like an intuitive reader, selecting the most plausible continuation from multiple choices. The model constructed 4 input sequences for each example, concatenating the given sentence with each possible continuation, and using the CLS representation to score options through a softmax layer. BERT Large achieved remarkable performance, outperforming the previous eSIM plus Elmo baseline by 27.1% and OpenAI GPT by 8.3%, demonstrating strong common-sense inference capabilities. Ablation studies revealed the critical importance of both pre-training tasks, with their removal affecting performance like removing essential ingredients from a carefully balanced recipe. When the next sentence prediction task was eliminated, performance dropped significantly on QNLI, MNLI, and Squad 1.1, while replacing the masked language model with left-to-right language modeling caused substantial degradation across all tasks. Even adding a bi-LSTM layer to strengthen the left-to-right model couldn't match the bidirectional pre-trained versions, confirming the fundamental importance of bidirectional context. Model size experiments demonstrated that larger architectures consistently improved performance, like increasing the size of a telescope to see distant objects more clearly. The researchers trained models with varying numbers of layers, hidden units, and attention heads, finding that even BERT Large's 340 million parameters showed continued improvements over BERT Base's 110 million parameters across all datasets. Remarkably, these improvements held even for small datasets like MRPC with only 3,600 training examples, suggesting that sufficient pre-training allows large models to benefit small-scale tasks substantially. The scaling effects proved particularly noteworthy because they represented some of the first convincing evidence that extreme model sizes could dramatically improve very small-scale tasks, like using industrial equipment to perform delicate craftswork with unprecedented precision. Previous work had shown mixed results when scaling pre-trained models, but BERT's approach of fine-tuning all parameters rather than using feature-based approaches appeared crucial for realizing these benefits. The researchers hypothesized that full fine-tuning allowed the large pre-trained representations to adapt more effectively to downstream tasks than approaches that kept pre-trained parameters frozen. BERT's introduction in 2018 fundamentally changed the landscape of natural language processing, establishing bidirectional pre-training as a cornerstone technique that would influence years of subsequent research. The model's success demonstrated that carefully designed pre-training objectives, combined with sufficient scale and bidirectional context, could create representations powerful enough to achieve state-of-the-art performance across diverse tasks with minimal task-specific modifications. This work laid the groundwork for the transformer-based language models that would dominate NLP in the years following its publication, making it a landmark contribution to the field. And here we are at the end of our gentle journey together, having traced this remarkable transformation from BERT's bidirectional understanding through RAG's combination of parametric and non-parametric memory, through few-shot learning and foundation models like NEXUS, all the way to the agentic systems that can reason across your organizational silos. Those 40 fraud and risk models you built with such care, they served their purpose in their time, But now you can see how foundation models combined with agent logic offer a different path forward. You don't need to carry the weight of every technical detail we've covered tonight. Simply rest in the knowledge that change, even profound change, happens gradually and with purpose. Sleep well, knowing that tomorrow brings new possibilities for building intelligence that truly serves your organization's needs.